Hello, this is Dr. Dave again, and we are talking about interactions between two continuous variables. So here's where we're going to be going. We're going to start at the end and show you a graphic of the results from a hypothetical data set that I made up. So research has shown that people who are high in the belief for a just world, that is, they believe things such as they believe in Protestant work ethic, such that if you do the work that's required, you're going to end up on top financially. They believe that if bad things happen to you, that you must have done something to deserve it. That is basically the idea of a belief in a just world. And what you see here in this graphic is that we're looking at jury decisions, and the idea is that if a person is more attractive, the jury's going to be more likely to hold them less responsible. The notion being that, of course, attractiveness, people must be good, and people who have a belief in a just world must believe that more. And so the higher the attractiveness, the less number of years that they are going to be sentenced to. The lower the attractiveness, the more likely it is that they must have done it. So looking at the results here, we have defendant's attractiveness on a continuum as one predictor. We have judges' belief in a just world as another predictor. This predictor is continuous, and so what has to happen is you have to represent that choosing a couple of points. And the points that we've chosen here are those of being at the mean, that's the green line. The blue line represents being one standard deviation below the mean, and the red line refers to being one standard deviation above the mean on judges' belief in a just world. And so what you're seeing here is that particularly when the defendant is unattractive, and there's the notion of an interaction with the and the judge believes in a just world, that they are giving it's unattractive and they believe in a just world, they're giving a much larger sentence to the defendant. You notice on the blue line that for people who don't believe in a just world, attractiveness isn't having that big of an effect. If you look at the green line, you see on average that people at the average of belief in a just world, the more attractive, the less the sentence. So everyone's kind of moving in that direction. So you basically see evidence of a main effect here, that defendant's attractiveness leads to a reduced likelihood of a significant sentence in terms of number of years. This is, as we'll learn at the end of this tutorial, specified using a Johnson-Newman analysis. What a Johnson-Newman analysis does is to find the point at which the slopes start to become significant. So you'll notice that this line here, which I specify in my notes down over here, is a score on the just world belief of 3.376. That going above these slopes, which would represent 63% of all possible slopes, filling out the area, is those slopes are statistically significant. slopes that are below that are not statistically significant. Now, this is the way that a Johnson-Newman analysis Johnson-Niemann analysis is generally presented. It's generally done with just the moderating factor. What I did here was to add on to that my own little twist, and that is I did it on the dimension of attractiveness as well. And so if you flip it, and it is easier to see if you flip it, and we'll go back to that at a later point here. If you flip it, you find that when attractiveness is working as the moderator, 67% of the slopes that are where the person is attractive more than a 3.34, that is not statistically significant. They are statistically significant, the 33% of the slopes that would be very unattractive at 3.34 and below. So I like this graph in that it really highlights that this area right here, this section right here, is where attractiveness or lack thereof and belief in a just world are really combining to separate people out for mostly. Now, what's the math that got us here? How do we use process to get this graphic? That's where we're headed, and I'll be moving there in just a second. Okay, I want to take a look at the data and then run a quick analysis, show it to you without centering and with centering, and then talk about how we move to finding the simple slopes. So here's the data set. It's just 27 observations. You have attractiveness, where the attractiveness of the defendant is judged on a 1 to 10 point scale, 10 being most attractive, 1 being least. Just world beliefs or go from 1 to 9, 9 being the highest, and then number of months that the defendant is sentenced, going from a low of 8 to 38. It could be months, it could be years, it doesn't really matter as it's all made up, but whichever one floats your boat. So I'm going to have to start by getting interaction terms. So I'm going to go over here to syntax, and I'm going to compute an interaction term simply by multiplying attractiveness by just world beliefs. And so when I do that, I'm going to go ahead and put an execute statement in here. And when I do that, you get a new column, interaction, being the multiplication of attractiveness in just world. So 2 times 1 is 2, 3 times 2 is 6, and so forth. Let's go ahead and run the regression. I'm going to go and do this hierarchically. I'm going to put in sentence as the DV. I'm going to put attractiveness and just world as my independent variables. And then next I'm going to put in the interaction term and then run. Comes out in 2 steps. The first step is significant. The second step is significant. The first step added 27.6% explained 27.6% of the variability. The interaction explained 11.9% of the variability. Both were significant. That first step I have shows that attractiveness, the more the attractiveness, the lower the sentence given. So that's a beautiful uh, implies goodness uh, stereotype. And then just world belief is not showing up to be significant there. So by itself, just world belief not doing anything. It's interesting to look and see how this changes. So when attractiveness um, is now controlling for the interaction effect. The interaction effect is statistically significant, but attractiveness is no longer significant, and now just world beliefs is significant. But keep in mind that that means that just world beliefs is significant when the when attractiveness is zero, and zero is not even on the scale, right? Attractiveness went from 1 to 10. So when attractiveness is equal to zero, just world beliefs are having an effect. When just world beliefs are equal to zero, attractiveness is having no effect. But then there's nobody that has that. So these are, artificial. So in this context, it's better to think that, to trust uh, the effects that are given up front before the interaction term is put in, and to trust that attractiveness has the negative effect. That said, the interaction requires that we privilege the interpretation of the simple slopes that make up the interaction and not the main effects. Okay, so what happens when we go ahead and center the data? So I'm going to go ahead and run data sort cases. Yep. I'm going to run analyze descriptive statistics, put in attractiveness and just world beliefs. And I find that the mean for attractiveness is 5.037. The mean for just world beliefs is 4.8148. And so I want to use those means for centering. So here I have compute center attractiveness equals attract minus the 5.04, rounding off a little bit. And the just world beliefs, compute just center just world equals just world minus 4.81, and then centered attractiveness is the multiplication of those two centered scores. I don't have to center it itself, just multiply together the centered scores, because 0 times 0 at the centers will equal 0. So centered attractiveness is going to take care of itself once you're using the centered scores. I'm then going to run this regression where I put in centered attractiveness and centered just world beliefs first, and then put in the interaction term. I'm just going to go ahead and run these all together. When I do that, the centered attractiveness shows up in the data set, centered just world shows up in the data set, the centered interaction shows up in the data set. Let's look at our output for the regression. What we get in terms of the model summary statements, where we're looking at our change in R squared, and the F change values is exactly the same thing that we got with the uncentered score, reminiscent of what we've been talking about in the last several sections of the course. When I go down here and look at centered attractiveness and centered just world beliefs, I get exactly the same thing that I had in step one with the uncentered. Once I put in the centered interaction term, notice that these are not changing dramatically. Centered just world beliefs is still non-significant. Centered attractiveness is still significant. So what centering did is it allowed for me to put in the interaction term and for the interaction term to not mess up the interpretation of the main effects. Now, from here, the question is, how do we get the simple slopes? Our basic equation is this: y hat equals b0 plus b1x plus b2z plus b3x times z. I'm going to use x as my key predictor. I'm going to use z to represent the moderator, but it's another continuous variable in the model. And then I'm going to multiply x times z together. That gives me my interaction term. So I have b1 for the main effects of x, b2 for the main effect of z, and b3 for the interaction effect. Now I'm going to go ahead and re-express this equation. So I'm going to take my b2z and take it and put it over here. And I'm going to take my b1x and put it over here. And I have skipped a step here. I've already jumped to factoring out the x value. So it would initially read b1x plus b3x times z. But then on the next step, what I'm going to do is combine those terms and then factor out the x. This now positions me to obtain a intercept and a slope with respect to x, using various levels of z to change the equation as appropriate based upon how z actually moderates the relationship of x to y. And what's most important to recognize here is that if z is 0, the equation simplifies pretty easily. If z is 0, the b2 cancels out. If z is 0, the b3 cancels out. And hence, I am left with b0 plus b1x. So this tells me that my initial value of b0 and my initial value of b1 represent the relationship of x to y when z is equal to 0. If the data are centered, then b1 is not just when z is 0, it's when z is at the average level of z. Because that's the idea of centering, is it makes those other predictors at their average when the value is equal to 0. So this is really, so my simple slope is easy for the average. Just center z, compute everything, and you're good to go. It's going to simplify into a B0 and a B1 because everything else is multiplied by 0. This gives me my regression line when Z is at its average. So when people are average on just world beliefs in this case. But I need indications of how that slope is varying from when Z is not 0. So when people get high, are high on just world beliefs, where's the slope? When people are low, where's the slope? Now, conceptually or conceivably, you could sit there and get, you know, move the value at, you know, a single point or a tenth of a point. You could go a tenth of a point above the mean, another tenth, another tenth, another tenth, another tenth. Every time you move a tenth of a point above the mean, you could compute a new slope. What would that would give us is a whole array of slopes, a fan shape array of slopes. It's a little bit much, maybe a lot too much. And for that reason, what we do is we tend to choose a couple of points for graphing our slopes. And most commonly, what's been done is to choose one standard above the mean on Z and one standard deviation below the mean on Z. So if I go ahead and look up my standard deviation for Z, once my data are all centered, I basically plug that standard deviation in and multiply it times B2. That tells me how much my intercept is changing. Take the standard deviation of Z, multiply it by B3 here in this in the second half of the equation, where this deals with where B3 tells me how my slope is changing as a function of Z. And that gives me a slope at one standard deviation above the mean on Z. Take the standard deviation and multiply those values by the negative of the standard deviation. So -1 times the standard deviation. So it would give you the one standard deviation below the mean. And this is going to tell you how the intercept is changing at that place. And this will tell you how the slope is changing at that location. Here's my equation written out. So it originally came out as 26.81 plus a -1.8 for centered attractiveness plus a 0.75 for centered just world beliefs plus a minus 0.397 for the interaction term. Centered attraction times centered just world beliefs. Go ahead and reorganize that information. So go ahead and take my just world beliefs over here, my centered attractiveness go over here, and factor out centered attractiveness, and I have my reduced form equation. Find the standard deviation for just world belief. That happens to be 2.69. Plug in the 2.69 here, plug in the 2.69 here. So over on this side of the equation, we start off with 26.81, which is the intercept, not considering just world belief, or when just world belief is at its average. Then add 0.75 times the 0.269. This gives me 28.83, my new intercept. Take your initial slope for centered attractiveness of -1.8 and add to that the interaction term to tell me how much the slope is going to change. That's -0.397 multiplied by centered just world beliefs, of 2.69, and I get a minus 2.87. I now have, for one standard deviation above the mean on just world beliefs, a intercept and a slope. And once you have an intercept and a slope, all you need is a couple of points and you can plot the line. Here we have centered just world beliefs at the mean of 0. So I have 26.81 plus 0.75 times 0. That cancels out. This leaves me with my 26.81. Over here for the intercept, the minus 0.397 tells me how the intercept is going to change. But at this particular point, when centered with centered just world beliefs telling me where people are at the average, it centers with 0 being there, it cancels that out. So my slope is just minus 1.8 times centered attractiveness. And then finally, for centered just world beliefs below one standard deviation, take that standard deviation of 2.69, multiply it by minus 1, then take that negative term, multiply it times 0.75, add it to my 26.81, I get 24.79. That tells me my new intercept. And over here, take the minus 1.8 plus the minus 0.379 times minus 0.269. That solve all of that. That gives me my new slope. So we're using the reduced form equations to find a new intercept and a new slope. That gives us the equations for 3 lines, 3 simple slopes. All you then need is points, and you can graph this out. And you get a graph that is, in rough fashion, what we saw from the graphic I started this lecture with. So for my 3 points, I centered attractiveness has a standard deviation of 3.8. So I basically went out just a little bit beyond one standard deviation on the left, beyond one standard deviation. One standard deviation on the left, on the negative, one standard deviation out on the right. Plugged in minus 3, 0, and 3 into this centered attractiveness, solve the equation. Each time I solved it, it gave me then a, respectively, for those values, a 37.44, a 28.83, a 20.22. I plotted the line. Over here. I plotted the line. And with that information, I plotted the line, and that gives you your simple slope for the people high in belief in just world. I did the same thing for the next equation. Use those points to plot the line. I did the same thing for the next equation. Use those points to plot the line. And that gives me my figure. And that's the math and the ideas behind coming up with your simple slopes. What we next need to do is to figure out how to do this more precisely or easily with the computer. And while it's easy enough to get the slopes by hand or even in Excel, the problem we face is getting the correct standard errors for being able to do significance testing to be able to determine, are the slopes significantly different? So we will turn to that in the next section.